Welcome back, traveler of the space. Before galaxies, before light, before even time itself, there was nothing. And then, in a single, powerful moment, everything began. This was the Big Bang, the event that gave birth to space, time, matter, and energy. From a point smaller than an atom, the entire universe expanded outward, setting the stage for every galaxy, star, and planet that would ever exist, including our own. Tonight, we'll travel back to that very first moment. We'll explore how the universe began, how it grew, and how we can still see the afterglow of its birth in the night sky. So, take a deep breath, and let's journey to the beginning of everything, to the moment when the cosmos itself took its very first breath. Around 13.8 billion years ago, something extraordinary happened, the beginning of everything. This event is what scientists call the Big Bang. Despite the name, it wasn't an explosion in space. It was the sudden expansion of space itself. Everything that would ever exist, every atom, every particle, every galaxy, was once packed into an unimaginably small and hot point, often described as a singularity. From that tiny, dense origin, space began to stretch and expand in all directions, setting the universe into motion. At the very start, the universe was incredibly small, much smaller than an atom. Yet it contained all the energy and matter that would one day form stars, planets, and life. Temperatures were unimaginably high, and energy was so intense that particles couldn't even form properly. Instead, the universe was a thick, glowing soup of energy-pure radiation. In this first moment, time and space themselves came into existence. Before the Big Bang, there was no before, because time itself began at that instant. Asking what came before the Big Bang is like asking what's north of the North Pole. There's no meaningful answer, because time began with that event. In the first tiny fraction of a second, the universe expanded at a rate faster than the speed of light, in a phase called cosmic inflation. During inflation, space itself stretched exponentially, smoothing out the universe and making it roughly uniform in every direction. This inflationary burst took less than a trillionth of a second, but shaped the entire structure of the cosmos. Tiny quantum fluctuations, minute differences in density at the smallest scales, were stretched out by inflation to cosmic sizes, becoming the seeds from which galaxies and clusters would later grow. After inflation ended, the universe continued to expand, but more slowly. The immense energy that filled space began converting into matter and radiation. The universe was still unimaginably hot, trillions of degrees, but as it expanded, it began to cool. In the first second of its existence, the basic building blocks of matter, quarks, electrons, and neutrinos came into being. Quarks joined together to form protons and neutrons, the components of atomic nuclei. The universe was filled with a dense fog of these particles, constantly colliding, breaking apart, and reforming. About 3 minutes after the Big Bang, the universe had cooled enough for these protons and neutrons to fuse together in a process called nucleosynthesis. This is when the first atomic nuclei were created, mainly hydrogen, helium, and tiny traces of lithium. These light elements still make up almost all the normal matter in the universe today. But even though the nuclei existed, atoms as we know them couldn't form yet because the universe was still too hot for electrons to stay attached. For hundreds of thousands of years, matter existed as a glowing plasma, a mix of free protons, electrons, and light. During this period, light couldn't travel far without being scattered by the free electrons, so the universe was opaque. No light could move freely through it. It wasn't until about 380,000 years after the Big Bang that the universe cooled enough for electrons to combine with protons to form neutral atoms. This moment is known as recombination, and it was a turning point. For the first time, light could travel freely through space. That ancient light is still around us today, and we can detect it as the cosmic microwave background radiation, a faint glow that fills the universe and serves as a snapshot of that early moment. The cosmic microwave background is one of the most important pieces of evidence for the Big Bang. It's like an ancient photograph of the universe when it was just a baby, only a few 100,000 years old. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB showed that the universe was once filled with a nearly uniform glow of radiation. Tiny variations in the temperature of this glow, only a few millionths of a degree, correspond to small differences in density. These differences later grew into galaxies, stars, and clusters under the influence of gravity. Without those early ripples, the universe would have remained smooth and featureless. As millions of years passed, gravity began pulling together the slightly denser regions of gas into clumps. These clumps grew larger and denser until the first stars ignited. When the first stars were born, they flooded the universe with light, ending what astronomers call the cosmic dark ages. These early stars were huge and short-lived, burning brightly and then exploding in spectacular supernovae. Those explosions released heavier elements into space, seeding the material for the next generations of stars and planets. From this cycle of birth and death, the structure of the universe began to take shape. The galaxies we see today, like the Milky Way, are descendants of those first clusters of matter formed after the Big Bang. Over billions of years, small galaxies merged into larger ones, and stars continued to form and die, enriching the universe with the elements necessary for life. Our own sun and solar system are part of that story. The atoms in your body, carbon, oxygen, calcium, and iron were forged in earlier generations of stars that were themselves the descendants of the first hydrogen and helium made minutes after the Big Bang. In that sense, the Big Bang isn't just a distant event. It's the origin of everything that makes us who we are. The Big Bang Theory doesn't just explain how the universe began, it also explains what we observe today. The expansion of space, the cosmic microwave background, and the abundance of light elements all fit perfectly into the Big Bang model. Every observation we make strengthens the evidence that our universe has been expanding and cooling for billions of years. When we look deep into space with powerful telescopes, we see galaxies moving away from us, and the farther they are, the faster they're receding. This observation, first made by Edwin Hubble in the 1920 seconds, was the clue that led to the realization that the universe is expanding, and that expansion must have started from a single point. Even though we understand a lot about the Big Bang, there are still mysteries that scientists are trying to solve. For instance, what caused the Big Bang to happen in the first place? What triggered the inflationary expansion? Why does the universe contain more matter than antimatter? And what exactly is dark energy? The mysterious force driving the universe's accelerated expansion today. These questions remind us that the Big Bang was not the end of the story. It was just the beginning of an ever-unfolding cosmic journey. The more we study it, the more the Big Bang becomes not just a scientific concept, but a story of creation, a story of how the universe went from nothing to everything. It's the ultimate origin story, written not in words, but in light, matter, and space itself. Each discovery brings us a little closer to understanding how time began, how galaxies formed, and how life emerged in a universe that started as a blinding burst of energy. After the first few 100 million years, the universe began to take on a more recognizable structure. Space was still expanding, but inside it, gravity was slowly gathering matter into enormous clouds of gas. These clouds became the birthplaces of the first galaxies. The earliest galaxies were smaller and more irregular than the majestic spirals and ellipticals we see today. Over time, they collided and merged, creating larger galaxies with billions of stars. This was the age when the universe was learning to organize itself. Gravity pulled matter together, while the expansion of space kept things from collapsing entirely. This delicate balance between gravity and expansion shaped the cosmos. The Big Bang Theory also tells us that the universe has no center and no edge. Every point in space is expanding away from every other point. Imagine dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from all the others, but none of them are at the center of the expansion. That's how space itself behaves. It's not that galaxies are flying through space away from a central explosion. Instead, space itself is stretching, carrying galaxies with it. This is why no matter where you are in the universe, you would observe other galaxies moving away from you. The expansion of space is everywhere and affects everything on the largest scales. As the universe continued to expand and cool, more and more complex structures appeared. The first stars were enormous, much larger than our sun, and they burned through their fuel quickly, often exploding after just a few million years. These explosions spread heavier elements like carbon, oxygen, and iron into the surrounding gas. The next generations of stars formed from this enriched material, giving rise to planetary systems with the ingredients for life. In this way, the Big Bang indirectly made life possible by setting in motion the chain of events that produced stars, planets, and elements. The discovery of the expanding universe came from the work of astronomer Edwin Hubble in the 1920 seconds. He studied distant galaxies and found that their light was stretched toward the red end of the spectrum, a phenomenon called redshift. This meant the galaxies were moving away from us. The farther away a galaxy was, the faster it was receding. This pattern could only mean one thing: the universe itself was expanding. If everything is moving apart now, then long ago, everything must have been closer together. When you rewind that expansion backward in time, all the matter and energy converge to an initial state, a hot, dense beginning, just as the Big Bang describes. Hubble's discovery revolutionized our understanding of the cosmos. Before him, most people thought the universe was static and eternal. Even Albert Einstein had originally introduced a cosmological constant into his equations of general relativity to keep the universe from collapsing or expanding. When Hubble's data proved that space was expanding, Einstein reportedly called his earlier assumption his biggest blunder. His equations, left alone, had already predicted an expanding universe. The Big Bang became the natural explanation for what Hubble and others observed. The 20th century brought many more discoveries that confirmed and refined the Big Bang theory. The detection of the cosmic microwave background radiation in 1965 was one of the strongest pieces of evidence. That faint glow was the leftover light from the moment the universe became transparent. Scientists measured its temperature about 2.7 Kelvin, just a few degrees above absolute zero, and found it matches almost perfectly with what the Big Bang model predicts. This discovery earned Penzias and Wilson the Nobel Prize in Physics and solidified the Big Bang as the leading explanation for the origin of the universe. Later observations by satellites such as COBE, WMAP, and Planck mapped the CMB with incredible precision. These maps show that while the early universe was mostly uniform, it had tiny fluctuations, minute temperature differences that reveal how matter was distributed. Those tiny differences, only 1 part in 100,000, were enough for gravity to pull matter together over billions of years to form galaxies, stars, and planets. The pattern of these fluctuations also tells scientists a lot about the shape, age, and composition of the universe. According to current measurements, the universe is about 13.8 billion years old and is made up of roughly 5% normal matter, 27% dark matter, and 68% dark energy. The Big Bang theory also predicts that the universe should be filled with light elements, mostly hydrogen and helium, in specific ratios. When astronomers measure the chemical composition of stars and galaxies, those ratios match the predictions almost perfectly. About 75% of the ordinary matter in the universe is hydrogen, 25% is helium, and only a tiny fraction is heavier elements. This too fits beautifully with the idea that those elements were forged in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion to occur. As scientists refined their models, they began to explore deeper questions about what the Big Bang really means. Was it truly the beginning of everything? Or was it just the start of our observable universe? Some theories suggest that the Big Bang might not have been the absolute beginning, but rather a transition from a previous state, a bounce from an earlier collapse, or a fluctuation in a larger multiverse. These ideas are speculative, but they show how the Big Bang opened up profound questions about the nature of reality itself. The idea of the Big Bang has also influenced philosophy and human thought in surprising ways. For much of history, people assumed the universe was eternal and unchanging. The Big Bang, however, suggests a definite beginning, a moment when time and space started. That concept resonates with ancient creation stories, but it's grounded in physics and observation. It raises deep questions. If the universe had a beginning, what caused it? Can something come from nothing? Does the universe have an end? These are questions that stretch beyond science into the realms of philosophy and imagination. Despite the mysteries, what we do know is breathtaking. The Big Bang explains how a universe that began smaller than an atom became vast beyond comprehension. It explains why the night sky glows faintly with ancient light, and why galaxies are rushing apart even now. Every atom in your body, every bit of matter in the stars and planets was once part of that early, seething fireball. The story of the Big Bang is, in a sense, the story of us all. Even now, the universe continues to expand, carrying galaxies farther apart as time goes on. The same laws of physics that governed the first moments after the Big Bang still shape everything today, from the spin of electrons to the dance of galaxies. We are living in a universe that is still echoing the event that gave it birth. The cosmic background radiation is a whisper from that time, a faint memory of the moment when everything began. And though we may never fully understand what triggered the Big Bang, or what lies beyond the edge of our knowledge, we continue to learn more with every observation. Each new telescope, each deeper look into space, takes us further back in time, closer to that mysterious first instant when the universe began to exist. As we continue the story of the Big Bang, it's fascinating to think about how scientists can study something that happened nearly 14 billion years ago. We can't travel back in time, but light allows us to look into the past. When we observe distant galaxies, we're actually seeing them as they were billions of years ago, because their light has taken that long to reach us. The farther we look, the closer we get to the beginning of time. Modern telescopes like the James Webb Space Telescope have allowed us to peer deeper into the universe than ever before, capturing light from galaxies that formed only a few 100 million years after the Big Bang. These early galaxies appear smaller, fainter, and more chaotic, helping scientists understand how the first structures took shape in the young cosmos. The universe wasn't always filled with stars and galaxies like we see today. For the first few 100,000 years, as we've seen, it was a sea of hydrogen and helium atoms. Then, as the first clumps of matter grew under gravity's pull, the earliest stars began to ignite. This period is called the epoch of reionization because the light from those first stars and galaxies reionized the gas that filled space, making it transparent once again. It was like turning on the lights in a dark room. The first stars were incredibly massive and short-lived, burning hot and bright before exploding as supernovae. These explosions scattered heavier elements into space, enriching the surrounding gas and paving the way for future generations of stars, planets, and possibly life. The light from those early times is still reaching us today, stretched by the expansion of the universe. When light waves travel through expanding space, their wavelengths get stretched, making them redder, a process known as cosmological redshift. This is different from the redshift caused by motion. It's not that galaxies are moving through space. It's that space itself is expanding, and the light traveling through it is stretched. This stretching of light is how scientists measure how far away objects are and how fast the universe is expanding. It's one of the key ways we know that the Big Bang is still ongoing in the form of cosmic expansion. But what powered the Big Bang? What made the universe expand so violently in the first place? This is one of the biggest mysteries in science. The concept of inflation, proposed by physicist Alan Guth in the early 1980 seconds, helps explain many puzzles about the early universe. Inflation theory suggests that a fraction of a second after the Big Bang, the universe expanded exponentially much faster than the speed of light. This doesn't break the laws of physics, because it wasn't matter moving faster than light, but space itself expanding. During this brief moment, the universe smoothed out, which explains why it looks roughly the same in all directions today. Inflation also explains why galaxies are distributed the way they are. Tiny quantum fluctuations that occurred during inflation became the seeds of all large-scale structures in the universe. Still, inflation raises its own questions. What caused it to start and stop? Some theories suggest that inflation might be part of an endless process, creating multiple universes or pocket universes in a vast cosmic foam. This idea is called the multiverse. In such a model, our universe might be just one of countless others, each with its own laws of physics and conditions. We may never be able to test this idea directly, but it shows how far the Big Bang Theory has pushed human imagination. The more we learn, the more we realize how much remains to be discovered. One of the biggest pieces of evidence for the Big Bang came from something unexpected: radio noise. In 1965, Arno Penzias and Robert Wilson were using a radio antenna to study signals from space. They kept detecting a faint, uniform hiss no matter where they pointed their instrument. At first, they thought it was interference or even pigeon droppings inside the antenna. But after cleaning it and checking everything, the noise remained. What they had found was the cosmic microwave background radiation, the afterglow of the Big Bang. That faint signal confirmed what theorists had predicted years earlier. The universe was once hot and glowing, and its light has been cooling ever since. Today, that ancient radiation is all around us, coming from every direction. If your TV set picks up static when it's not tuned to a channel, a tiny fraction of that static is actually the leftover light from the Big Bang. When scientists study the cosmic microwave background in detail, they find a pattern of tiny temperature variations, ripples, that correspond to areas of slightly different density in the early universe. Those ripples are the fingerprints of the first structures that would later become galaxies and clusters. By analyzing them, scientists can determine the age, shape, and composition of the universe with extraordinary accuracy. Measurements of the CMB reveal that the universe is almost perfectly flat, meaning the geometry of space follows the rules of Euclidean geometry. Parallel lines never meet, and the angles of a triangle add up to 180 degrees. This flatness is another clue that supports inflation theory, which predicts that the rapid expansion of space would stretch the universe into a flat shape. It also helps scientists estimate the total amount of matter and energy in the cosmos. Remarkably, all the normal matter, everything made of atoms, makes up only about 5% of the universe. The rest consists of dark matter and dark energy, two mysterious components that we can't see directly, but whose effects we can observe. Dark matter acts as an invisible glue, holding galaxies together and shaping large-scale structures across the universe. Without it, galaxies would fly apart because there isn't enough visible mass to create the necessary gravity. Dark energy, on the other hand, appears to be driving the acceleration of the universe's expansion. In other words, while gravity tries to pull things together, dark energy pushes them apart. The discovery of dark energy in the late 1990 seconds came as a huge surprise and has since become one of the biggest mysteries in cosmology. Scientists think it may be related to the energy of empty space itself, but no one knows for sure. The story of the Big Bang is, in many ways, the story of discovery. Every generation of scientists builds on what came before, using better tools and sharper minds to push the boundaries of knowledge. What began as a bold idea in the early 20th century is now one of the most well-tested theories in science. Yet, the Big Bang doesn't answer everything. It opens the door to deeper questions. why does the universe follow these specific physical laws? Why did matter win over antimatter in the early moments? What existed, if anything, before the Big Bang? These are questions that may take centuries or perhaps forever to answer. Still, the Big Bang Theory gives us a powerful framework for understanding how we got here. It connects everything from the tiniest particles to the largest galaxies into one coherent story. It shows that the universe is not static, but dynamic, constantly changing and evolving. It tells us that we are part of a cosmic process that began nearly 14 billion years ago and continues to unfold even now. The atoms in our bodies were once part of that glowing fireball, cooled and shaped over eons into stars, planets, and life. When we look up at the night sky, we're not just seeing distant stars, we're seeing the ancient light of creation itself. Over billions of years, the universe has evolved from a chaotic, hot soup of particles into the structured cosmos we see today. This transformation didn't happen all at once. It was a long, slow process shaped by the interplay of gravity, radiation, and time. After the Big Bang, the universe was dominated by radiation. Photons, or light particles, carried most of the energy. As it expanded and cooled, matter began to dominate. Gravity started to pull together regions that were slightly denser than their surroundings, forming the first cosmic structures. It's astonishing to think that the tiny ripples in the density of the early universe, visible today in the cosmic microwave background, eventually grew into the immense clusters of galaxies that span billions of light years. The first galaxies probably formed a few 100 million years after the Big Bang. These early galaxies were small, chaotic, and packed with young, massive stars. Many of these first stars burned hot and died quickly, exploding as supernovae. These explosions were critical because they scattered heavier elements, carbon, oxygen, and iron, into the surrounding gas clouds. Those elements would later become the raw material for new generations of stars and planets. In this sense, every planet, every rock, and even every human body is made of material created in stars that lived and died long before the Earth formed. As galaxies grew, they began to merge and form larger structures. The Milky Way, our own galaxy, likely formed through a series of these mergers. By observing galaxies at different distances, astronomers can see different stages of this evolution, because looking farther away means looking further back in time. The most distant galaxies we've observed are so far away that their light began traveling toward us more than 13 billion years ago. When we look at them, we're witnessing the universe as it was only a few 100 million years after the Big Bang. It's like looking through a time machine made of light. The expansion of the universe never stopped. In fact, one of the most surprising discoveries in modern astronomy is that the expansion is not slowing down, it's speeding up. Scientists expected gravity to gradually slow the expansion, but in the late 1990 seconds, two independent teams studying distant supernovae discovered that the opposite is true. The universe's expansion is accelerating, driven by a mysterious force we call dark energy. This discovery changed everything. It meant that the universe's fate is not one of collapse, but of endless expansion. Over trillions of years, galaxies will drift farther apart until distant stars fade from view, leaving only the faint afterglow of a once bright cosmos. But that's far, far in the future. For now, the universe is still vibrant and full of activity. Stars are forming in vast clouds of gas. Galaxies are colliding and merging, and new worlds are being born. All of this traces back to the Big Bang, the ultimate starting point. The Big Bang wasn't just a single explosion. It was the creation of space, time, and energy that continues to shape everything around us. Even the laws of physics themselves, gravity, electromagnetism, nuclear forces, emerged in those first moments and have guided the universe ever since. Scientists have been able to reproduce many of the early conditions of the Big Bang in particle accelerators. By colliding particles at near light speeds, researchers can briefly recreate the extreme temperatures and energies that existed microseconds after the Big Bang. Experiments at the Large Hadron Collider LHC, for example, have helped confirm how matter gained mass through the Higgs field, a discovery that connects modern physics directly to the conditions of the early universe. These experiments give us a glimpse into how the fundamental forces and particles behaved when the universe was young. Yet, there are still deep mysteries. One of them is baryon asymmetry, or why there is more matter than antimatter. According to the laws of physics, the Big Bang should have produced equal amounts of both. When matter and antimatter meet, they annihilate each other, leaving only energy behind. But for some reason, there was a slight imbalance, about one extra particle of matter for every billion particles of antimatter. That tiny excess was enough to create all the matter in the universe today. Scientists don't yet know why this imbalance existed, but it's one of the key questions they're trying to solve. Another question concerns what happened before or beyond the Big Bang. According to our current understanding, time itself began at the Big Bang. So asking what came before might not even make sense. However, some theories suggest that our universe could have emerged from a previous state, like a quantum fluctuation or a bounce from a collapsing earlier universe. There's also the possibility that our universe is part of a much larger multiverse, where countless other universes are constantly being created and destroyed. While these ideas are still speculative, they remind us that the Big Bang might not be the ultimate beginning, but rather one event in an endless cosmic cycle. The concept of the Big Bang has also changed how humans think about our place in the universe. For most of history, people believed the cosmos was eternal and unchanging. The Big Bang revealed that everything has a history, a beginning, and possibly an end. It means the stars, galaxies, and even time itself are part of an evolving story. It also means we can trace our own origins back to the very start. Every atom in your body was once part of the hot, dense energy that filled the newborn universe. The calcium in your bones, the oxygen in your blood, the iron in your cells, all were forged in stars, which themselves were born from the ashes of the Big Bang. In this sense, the Big Bang is not just a scientific theory, it's a story of connection. It links everything in existence, from the tiniest particle to the largest galaxy, into one grand narrative. It shows us that the universe is not a random collection of things, but a single, unfolding event. Every moment of creation, every star that shines, every breath we take is part of that 13.8 billion-year-old process that began with the Big Bang. The universe continues to evolve, and we are one small part of its journey. Even though the Big Bang happened long ago, its echoes still fill the cosmos. The background radiation hums quietly in all directions, a faint reminder of that first moment. The galaxies continue to drift apart, expanding into the vastness. And here we are, tiny beings on a small planet, able to look back across billions of years and understand, at least in part, how it all began. That is one of the greatest achievements of human curiosity, the ability to comprehend the birth of the universe itself. When scientists talk about the Big Bang, it's easy to imagine it as a single explosive moment, but it's better understood as a continuous unfolding, a stretching of space that began everywhere at once. The name Big Bang can be misleading because it suggests an explosion happening at a point in space. But what actually happened was the rapid expansion of space itself. Every point in the universe today was once part of that same expanding fabric. If you could somehow rewind time, everything, galaxies, stars, even the empty space between them would shrink closer and closer together until the universe became so dense and hot that the laws of physics as we know them would break down. The first few fractions of a second after the Big Bang were dominated by pure energy. Temperatures were unimaginably high. Trillions of degrees and particles constantly collided and transformed into other particles. During this phase, known as the Planck era, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force may have been unified into a single force. As the universe expanded and cooled, these forces separated one by one, creating the distinct physical laws that govern everything today. We can't directly observe this period, but through theoretical physics and high-energy experiments, scientists have pieced together a picture of how the early universe behaved. After the first few minutes, the universe entered a calmer but still dynamic stage. The creation of the first atomic nuclei, mainly hydrogen and helium, was a crucial step. These simple elements formed the foundation for all matter that would come later. For hundreds of thousands of years, the universe was filled with a hot plasma of charged particles and light, constantly interacting. Eventually, as it expanded and cooled, electrons combined with protons to form neutral atoms, allowing light to travel freely for the first time. That released light became the cosmic microwave background, still visible today. In that sense, the Big Bang didn't just create matter and space, it created the very first light in the universe. As the universe continued to expand, gravity began to take over. Regions that were slightly denser than average started to pull in more matter, growing larger and forming the first structures. Over millions of years, these structures became the building blocks of galaxies. Inside those galaxies, the first stars ignited, creating bursts of light that ended the cosmic dark ages. These early stars were enormous, sometimes hundreds of times the mass of our sun, and they burned brightly but briefly. When they exploded as supernovae, they scattered heavier elements into space, beginning the process of chemical evolution that continues today. From those early generations of stars came new ones, along with planets and, eventually, life. The Big Bang didn't directly create life, but it set the stage for everything that would make life possible. It created hydrogen, helium, and trace amounts of lithium, the simplest elements. The stars turned those elements into heavier ones, like carbon, oxygen, and nitrogen. Those elements then combined in later stars, asteroids, and planets, eventually forming molecules like water and organic compounds. Billions of years later, on a small planet orbiting an average star, life appeared. When you think about it, the atoms in your body are ancient. They were once part of that original burst of creation. The Big Bang Theory is supported by a remarkable amount of evidence. Besides the cosmic microwave background and the expansion of the universe, another key piece comes from the abundance of light elements. Observations show that about 75% of normal matter in the universe is hydrogen, and about 25% is helium, with trace amounts of lithium. Those proportions match almost exactly what would result from nuclear fusion during the first few minutes of the universe's existence. If the Big Bang hadn't happened, or if it had unfolded differently, those numbers wouldn't match. This consistency gives scientists confidence that the Big Bang model is correct. Even so, the Big Bang is not the complete story. It explains how the universe evolved from a hot, dense state, but it doesn't explain what caused that state to exist in the first place. Was there something before the Big Bang? Or was the Big Bang itself the beginning of everything, including time? Some theories propose that the universe may have emerged from a quantum fluctuation, a random, spontaneous event where energy briefly appeared from nothing, following the laws of quantum physics. Others suggest that the universe might be cyclical, expanding and contracting endlessly in a series of big bangs and big crunches. These ideas are fascinating, but so far, there's no direct evidence to confirm them. The Big Bang also challenges our everyday understanding of space and time. In our daily lives, time moves in one direction, and space feels fixed and unchanging. But at the cosmic level, time and space are flexible. They bend, stretch, and curve in response to energy and matter. According to Einstein's theory of general relativity, gravity isn't a force pulling objects together. It's the curvature of space-time caused by mass. The Big Bang was the moment when space-time itself came into being. Before it, there was no before. At least not in the way we experience time. That's hard to imagine, but it shows how deeply the Big Bang reshaped our understanding of reality. Over the decades, many alternative theories have tried to replace or modify the Big Bang. Some, like the steady-state theory, propose that the universe had no beginning, and that new matter was constantly being created as it expanded. This idea was popular for a time, but eventually fell out of favor when the cosmic microwave background was discovered, proof that the universe had once been hot and dense. Other theories, such as ekpyrotic or cyclic models, suggest that our universe may have formed from the collision of higher dimensional spaces, or branes, in a larger multiverse. While these ideas are intriguing, the Big Bang remains the simplest and most supported explanation. What makes the Big Bang so powerful as a theory is that it connects the smallest scales, particles, and quantum energy with the largest scales, galaxies, and cosmic expansion. It links physics, chemistry, and astronomy into one grand narrative. It tells us not just where everything came from, but also how it continues to evolve. The universe we see now, with its billions of galaxies, is still expanding from that initial moment. In a sense, the Big Bang never really ended. It's still happening, just at a slower pace. The same laws that govern the early universe continue to shape its destiny today. When we study the Big Bang, we're really studying our own origins. The story of the universe is the story of us. Every star in the sky, every grain of dust, every atom in your body, all trace back to that first burst of creation. We are, quite literally, made of stardust, born from the ashes of the Big Bang. And even though we live on a tiny planet orbiting an ordinary star, we carry the memory of the universe's beginning within us. As we reach the final part of this journey through the Big Bang, it's worth stepping back and realizing just how incredible this story really is. Everything we see, touch, and know, all the galaxies, the stars, the planets, and even life itself, began from an unimaginably small, dense, and hot point about 13.8 billion years ago. The Big Bang was not an explosion in space, but the birth of space and time itself. It was the universe waking up, unfolding and stretching in every direction, setting in motion everything that would ever exist. The story of the Big Bang is not just about science, it's about existence, about how something emerged from nothing and how we, billions of years later, are able to look back and try to understand that beginning. After the first burst of expansion, the universe cooled, matter formed, stars lit up, galaxies assembled, and eventually, planets like Earth appeared. Over billions of years, gravity sculpted the universe into its current shape, a cosmic web of galaxies, connected by invisible threads of dark matter, all expanding within an ever-growing space, driven by dark energy. And all of this began as tiny ripples in the early universe, small differences in density that grew into the vast structures we see in the night sky. Those ripples, frozen in the cosmic microwave background, are like a baby picture of the cosmos, showing us what it looked like just 380,000 years after it began. The Big Bang also reminds us that the universe is not static. It is alive in a cosmic sense, always changing, always moving. Every second, space itself stretches a little more, carrying galaxies farther apart. In the distant future, galaxies beyond our local group will move so far away that their light will never reach us. Billions of years from now, future civilizations may not even be able to see evidence of other galaxies, making the universe appear small and lonely. But we live in a fortunate time, able to see both the past and the future written in the stars. Even though scientists understand much about the Big Bang, there are still many mysteries. We still don't fully understand what caused the Big Bang, or what existed, if anything, before it. We don't yet know exactly how dark energy and dark matter fit into the story, or what role quantum mechanics played at the very first instant. It's possible that the Big Bang was not the beginning at all, but just one chapter in a much larger cosmic cycle. Some theories suggest that our universe might be one of many part of a vast multiverse where countless other universes exist, each with different laws of physics and different beginnings. Maybe the Big Bang was just the spark that ignited our universe among infinite possibilities. But whether it was the absolute beginning or just one of many, the Big Bang connects us to everything. The energy released in that first moment still echoes across the cosmos as faint microwave radiation. The elements forged in the first stars now make up our world and our bodies. The light from ancient galaxies carries the memory of that first expansion. In every direction we look, we are seeing the past, each photon a messenger from billions of years ago, telling us the story of where we came from. When you look up at the night sky, you're looking into time itself. The faint glow of distant galaxies shows you the universe as it once was, long before Earth even existed. That light has traveled for billions of years, crossing unimaginable distances to reach your eyes. Every twinkle in the sky is a piece of history, a tiny echo of the Big Bang's grand symphony. It's humbling to think that the same universe that gave birth to galaxies also gave birth to us, the observers trying to understand it. We are not separate from the cosmos. We are its children, made from its stars, shaped by its forces, and powered by its energy. And so, the story of the Big Bang isn't just about physics or cosmology, it's about connection. It tells us that everything is related, that the atoms in your body once burned in stars that formed from the ashes of that first fireball. It reminds us how precious and rare it is for life to exist in such a vast, cold universe. Out of all the chaos and expansion, somehow order, beauty, and consciousness emerged. We, as thinking beings, are the universe's way of looking back at itself and asking, how did I begin? In the end, the Big Bang is both an ending and a beginning. It's the ending of nothing and the beginning of everything. It marks the moment when time began ticking and space began stretching. From that moment came galaxies, stars, planets, and life. The universe continues to expand, carrying its ancient story forward. And though we may never know exactly why it happened, we can marvel that it did. The Big Bang shows us that even from emptiness, something extraordinary can arise. That from a single spark, an entire cosmos can be born. And as you look at the stars tonight, remember that you are part of that same story. The light that began in the Big Bang still shines through you. You are a tiny but vital part of an ongoing cosmic journey that began 13.8 billion years ago and will continue long after you're gone. The Big Bang wasn't just the beginning of the universe, it was the beginning of you.